It's great to be here. My name's Mariel. This is my first time at Strange Loop, so it's been wild so far. Thanks. So I'm really excited to be here with you today, and I'd like to start by introducing myself. So I'm a particle physicist in my day job. I'm a postdoctoral researcher at Berkeley lab right now in California. A lot of my job involves making plots kind of like this one, analyzing data from the Large Hadron Collider at CERN. This is the largest particle collider in the world, and arguably one of the largest and most complicated machines humans have ever built. So I love my work, and my work involves building custom machine learning tools to help us better understand particles such as the Higgs boson that are fundamental to the universe. But I'm actually here today because I have an extensive background in the performing arts, so particularly in contemporary theater and dance. And thanks to motion capture technology, I've been able over the past few years to analyze my movements through the lens of a scientist and kind of bring my multiple loves together. So today I'm here as a performing artist who has worked with machine learning for a couple years, and I hope to talk about not only my research, but also some of the highlights and pitfalls of that journey so far. Basically this journey started in 2017, and since then I have led a couple of independent research groups working at the intersection of machine learning and choreography. So probably a lot of this audience would identify as creative types, I would imagine, in some form. So you might be familiar with a problem that I've often faced when improvising in the dance studio, which is that I find myself falling into a kind of creative rut where I'm returning to the same ideas over and over again. And this quote, which is by one of my favorite choreographers, the late Pina Bausch, really kind of summarizes it. I wondered if some of the machine learning techniques that I was working with in my job as a particle physicist could possibly apply to my art making and help me to generate fresh, new movements that were nevertheless in my own style. So I wasn't sure exactly how this would turn out. I had a couple of goals as I got started. I wanted the generated movements to look realistic, like a human being on Earth, preferably, with forces of friction and gravity present. I also wanted it to authentically look like my own style, whatever that meant to me. I wanted it to be movements that I probably would do in a studio. And more than anything, I was hoping for movements that would surprise me and inspire me to get up and moving, which is this final point, envie cinétique, which is kinetic desire. I just wanted something that would give me that desire to get up in a dance studio and move. So I should mention that the use of technology in dance has a long and interesting and rich history. And it's been spanning decades in the history of modern, postmodern, and contemporary dance. So many prominent choreographers in this discipline have used algorithms, equations, games of chance, motion capture even, and more to generate work over the years. So in some ways, what I'm presenting today is nothing new. In other ways, I would say, though, the incorporation of neural networks in particular and choreography is a relatively recent phenomenon, and it feels very cool to be one of the people who has been interested in pushing that specific intersection forward over the past few years. So when I started this project in 2017, there was some previous work in applying neural networks to choreography. So this gives you a sense of the state of the art at the time. So on the left is a project called Core RNN, and on the right is a project that was a collaboration between Google Arts and Culture and the choreographer Wayne McGregor. So both projects kind of have a similar model for the human body with around 15 to 20 points representing their motion. And both of them, I would say, had some difficulties capturing full three-dimensionality of a dancer's movements. The project on the left used an Xbox Kinect camera to detect a pose, which is a single camera facing front. So if your arm is occluded from the camera, it's difficult for the software to figure out where your body is. And on the right, they actually used video archives of McGregor's work and extracted poses from those two-dimensional video frames. So it suffered kind of the same difficulty. Both of them also used sequential models in machine learning that were designed for time series predictions. So we can kind of contrast those with the type of data that I was able to extract using Motion Capture Studio at my PhD institution that used a multi-camera setup of 20 different motion capture cameras. So you can see that it's really able to capture all the kinds of rotational motion that I might come up with in a studio. And I was also able to capture around 50 points on my body representing different areas. And this multi-camera setup allowed for nearly gapless data taking. So I could even roll on the floor, and it was able to interpolate where some of the points on my body needed to be at those points. So here's how we collected that data. It's the classic motion capture suit with a bunch of ping pong balls that are reflective all over my body. So they're collecting XYZ components for each of the points on my body at around 35 frames per second. So it's a pretty high-dimensional data set by some metrics. And so what I'll share with you today are 2 different projects that I led with different independent research groups. And together, we kind of pioneered the application of a couple different architectures in machine learning to motion capture of choreography. So the first project I'll talk about is a variational autoencoder, which is a VAE for short. And then the second project is a graph neural network, or a GNN. And sorry, I should say on the bottom is the multi-camera setup, where you can see all of the different camera angles that were viewing my movements. Great, so this first project is the variational autoencoder, and my research team was composed of many different types of experts. Some physicists who I collaborated with in my particle physics work, others who were interested in the digital humanities, and also some dance choreographers and researchers. And we worked together for a couple of years and then published our work in the summer of 2019. So the architecture that we designed is a variational autoencoder. And an autoencoder is a kind of machine learning architecture that tries to generate an output that closely replicates the inputs. And the catch is that often in these models, there's an information bottleneck that's built into the architecture. So here, you can kind of see this classic bow tie shape where the innermost layer of the model is highly reduced compared to the size of your inputs and your outputs. And so after quite a lot of iteration and training, eventually the model should find an efficient and lower dimensional representation of your input in that latent dimension. And moreover, the model that we built is a variational autoencoder, which sort of extends that basic autoencoder structure to allow for sampling and for generation of new material. So rather than learning a specific point to represent every input sequence that I showed the model learns a probability distribution for each of the latent dimensions present in the system. And then I sample from those latent probability distributions to then generate new material. So here are some examples of randomly sampling from the latent space of this model. So each of these movements are fully generated. And you can see that I think, in my view, they check the box of realism. They mostly look like humans existing on Earth. There's some kind of interesting artifacts and shaking sometimes, but I think for the most part, it was able to capture a lot of really nice, diverse and interesting movements, even though these might not be necessarily the most exciting movements that you could imagine doing in a dance studio. So I would say these are typical movements of the latent space. But what I was excited to try is to try sampling from parts of the latent space that were kind of on the fringes of the actual manifold of my real data. So sort of the areas that had less coverage in real data, and see what some of the more unusual movements that I could construct would look like. So that process is exactly what I did to construct the following video piece, which is also made up fully of generative movements. show the whole thing, unfortunately. So that was an example of sort of just working with the generated animations of the outputs. I'm also interested in live performance, kind of first and foremost. So I've had a couple experiences of trying to put those generated movements back onto a human body. So this was from a really early work in progress of having myself and a couple other dancers respond live on stage to some generated paths generated by the model. And then also my collaborator Raymond, who's a phenomenal dancer, did a performance in the motion capture studio itself where our data was collected. And that allowed him to get live feedback from the model in the following way. So projected on the screen, there are a couple different segments of what the model is responding to. So you can see his actual motion capture points in the middle. On the right is kind of where along, we call it like the phi rotational axis, so it's rotation around z, which angle he's facing. And on the left is maybe the most interesting, which is where in the latent space is his movement at any one time. And so as a dancer, his prompt was to play with staying in one area of the latent space and trying to figure out what movements belonged in that area versus traversing far across the latent space and trying to challenge the model in that way. So that was really fun. And that could have been maybe the end of the story, was generating new material with this model. But we also found another interesting way to put it to good use. So we found that beyond just generating outputs, this model was also pretty good at creating variations on existing phrases that I might find interesting as a choreographer, but might want to tweak in some non-trivial way. So this is kind of a cartoon of what this looks like, but because the model clusters related phrases together in the latent space, you can explore neighboring sequences in this latent material and then see how they align. So for example, the top two phrases that I've generated here both seem to share that they are on the floor, whereas these two movements on the bottom kind of share this timing of moving from crouch to standing. So there's kind of these interesting higher dimensional relationships that are shared between these different sequences. So we can exploit this fact in a really interesting way. So we can look at the specific latent embedding of a given sequence. So in this case, the black sequence here represents, it is my actual motion capture data that we use to train the model. Whereas in blue, we see the model's generated output representing this phrase. And you can see that the model's pretty well trained because it's captured a lot of the relevant kinematics that make this sequence kind of unique. But now if I take this latent embedding that the model has to represent this input phrase, and then I add a little bit of noise to that original point. So I kind of deviate from the original point and decode a new phrase that is nearby. Then the result is that I get a new movement that's very closely related to the original sequence, but has a modification. In this case, it's at the end of the sequence. You can see that the movement rotates a little bit. And you can imagine playing with this quite a bit. So if you deviate even further, you get a movement that still is related to the original kind of choreographic intent of that phrase, but deviates even further. So it's a fascinating exercise to trace how a single choreographic idea translates into something else as you move further and further from that original point. It was using this procedure that around last spring, at the onset of the pandemic, I was able to generate the following video, which is a duet with myself. So since I knew that I wasn't going to be able to dance in person with someone for a long time, it was something I was interested in doing early on. At the time, I thought that was going to be maybe a few weeks, and it ended up being a bit longer than that. So next, I'll show you an excerpt from a video of this duet with myself. So that sort of concludes the first, arch of this effort. And the story continues a little bit, which is that this past summer, I was an intern in Intel's AI group, and I was able to extend this work with a new set of collaborators. And they had expertise ranging from reinforcement learning to graph neural networks to generic deep learning. So the motivations for this study were a little different. So rather than just focusing on generating new material in the best way that we could, I was interested in turning the analysis inward and understanding relationships between different parts of my body while I danced. And this was exciting to me because this is actually what I think about when I dance, is how does my head relate to my feet? How are my muscles reacting to certain inputs? So I was curious to see what a machine learning model might tell me about some of those important relationships and whether they would necessarily align with the way that I actually feel like my body interacts with itself as I move. So technically, what that ended up resulting in is modifying the latent embedding of each given sequence to include an explicit graph structure representing each relationship between parts of my body while I moved. So essentially, it was a graph-based variational autoencoder. And graph neural networks, as a theme, are neural networks designed to operate on graph structures, where a graph here is a collection of nodes and edges, where edges represent relationships between those nodes. So then in the neural network structure, those features associated with each of the nodes and edges are then updated periodically by aggregating information from local subgraphs or neighborhoods near those points. The structure of the model was based on this project called NRI, or Neural Relational Inference, which is a project by Thomas Kipp, Max Welling, and quite a few others. And the idea of this is to learn a latent interaction graph to describe a dynamical system of interacting particles where you might not necessarily know all of the interactions that are happening. So in this case, for example, in this sort of toy model of a couple particles that are orbiting each other, you have each pairwise particle relationship assigned as one of some number of edge types, where edge types kind of means what's the quality of the interaction between these two particles. And that can include no edge, meaning that there's no relationship between those types. So, excuse me, our model, as in NRI, includes a graph neural network-based encoder and decoder. And the encoder's job is basically to output probability distributions for each of the edges that are present. So I input the same raw data that I used to train the variational autoencoder that I showed you guys previously, but in this case, I connect each of those points to every other point. So the model sees a fully connected input graph as its input. And then the encoder's job is to output a probability distribution for each of those edges about whether that edge belongs to edge type 0, edge type 1, edge type 2, or edge type 3. In this case, I chose 4 edge types. And then the decoder's job is to, once we sample from those probability distributions and get a discrete label for each of those edges, the decoder takes in those edge categorizations and then predicts the future kinematics of the system. So I'll show you some highlights of some of the relationships that the model learned. So in this case, edge type 0, which is on the left in pink, I've encoded to mean no interaction. And I've actually also imposed a prior distribution onto these different edge types such that 90% of the edges should be categorized as edge type 0. So I've asked the model to really be kind of sparse in the edges that it ends up highlighting for the actual kinematics of the system in hopes of making it a little easier to interpret. So most of the edges are categorized as no interaction. And you can kind of see that all of these, I've highlighted the top 1% of the edges that are kind of most representative of each edge. The most representative edge types of edge type 0, to me, don't really tell a clear story, which makes sense. But of the following 3 different edge types, they picked up on some interesting relationships. One that I found really exciting was in blue with edge type 2. So each of these edges that are most representative of this type of interaction originate in my right hand and then travel down to my left foot. And given that I have a background in ballet training, we talk quite a bit in ballet about opposition of arms and feet. And I'm also right-handed. I don't know whether to read into that or not, but it makes sense to me that my right hand would be pretty articulate, and that also the way that my hand moves affects the opposite leg in my body. And then there's also edge type 1 and edge type 3 that also describe relationships that all originate from kind of one localized area of my body, and then those have ripple effects that dictate movements in a very distant part of my body. So edge type 1, all of these edges originate in my left hand and then connect to my upper torso. Whereas edge type 3, these edges originate in my left foot and then extend up to both of my hands. So I found it really interesting that the model was picking up on these relationships that I might not have been able to write down based on my dance training, but that feel very authentically true to the way that I move. So we published this work last winter in the NeurIPS workshop on machine learning for creativity and design. I wish I had videos to show you of what performances with this work looks like, but I haven't had access to dancers or a dance studio for a number of years because of this pandemic. So instead, I did what any creator might do in this instance, which was make a TikTok account. And I was locked in my house, basically, so I was writing my thesis, and then as I was taking breaks on writing my thesis, I would get up and try to improvise using prompts from this model. So I have a couple clips of what that looked like. So on the left, I have a prompt from a highly ranked connection from the model. And in this case, that's a connection from the top of my head to my wrist, my right wrist. And so according to the model, this was a really important relationship to think about in generating my future movements. And I found that as an improvisational prompt, it was pretty useful. It was, yeah, playful, generative. I feel like I was having a lot of fun and thinking of movements that felt good. Then on the right, I tried a really lowly ranked connection. So this was a relationship between my left toe and my left knee, which there's a bone connecting those. It's really hard to play with that relationship. So I sort of interpreted it more broadly as relationships between feet and knees. So I was playing with these really awkward, weird feeling movements. So anecdotally, I felt like playing with these really got me out of my comfort zone in how I was thinking about creating some new work. All right, so last I'll just show a couple slides kind of summarizing what I've learned so far in this process. So the first is that I really thought that this process was going to have a single output, which was generating new sequences. And it had that, but I feel like it also had this kind of diverse array of uses that surprised me. So some of those uses beyond just inventing new material were kind of in the co-creative space of creating a dialogue with a model, iterating on that dialogue, and seeing how it might respond. And that involved creating these variations on existing sequences or even getting live feedback from the motion capture model in the studio. Another aspect that I haven't really talked about yet is a sense of preservation. The dance world does not have a universal written language to record movement or to even talk about movement. And so it's kind of difficult to think about how to preserve your creative practice as a dancer. Videos exist, but videos are often of performances that are just one instance of the thing, and it's not really capturing the real thing. So I've kind of come to think of these models as a way of preserving my creativity in this body that I have now, as a way of potentially being able to continue to invent with my creative practice right now, far into the future. And even though I haven't applied this yet, maybe there's a potential to apply this to historical documentation for other choreographers' practices as well. I've also learned that glitches are so awesome and appealing. I did not expect to be so I did not expect to be so delighted by undertrained models or, weird failure modes. So they can be hilarious. I've also found that they can just be beautiful. Ways that it can create these imageries that I could imagine trying to code for hours and hours. So they've been totally surprising in that aspect also. And then lastly, it's also taught me a couple different ways of conceiving of my relationship with a machine learning model in a creative context. And that kind of relationship was constantly shifting. And so that's kind of what I wanted to leave you guys with today. So this is just my personal mental map of how I've started to think about this relationship. So here, the y-axis kind of represents who has the creative power or the autonomy in this system. Is the model making those creative choices, or am I making those creative choices? And then along the x-axis, I have, is the model your friend, or is the model not your friend, whatever that might mean. And I feel like this project has spent some time in kind of each of these quadrants throughout its evolution. It's ranged from automating in the sense of just generating new material, and that's kind of the final result, to generating like a mountain of sequences, and then I can kind of cherry pick which phrases seem interesting to me, and then I craft a video piece out of those outputs. It's also served as kind of like an external eye critiquing my practice and showing me what it sees in the way that I move, sort of like an alien looking at my movements. And then at times, it has felt like it's having its own creative experience. It's responding to my movements, and it's creating a relationship between my previous movements and the current existence of that model. So all of these, I think in the future, I'm kind of most excited about this bottom left quadrant. And in particular, trying to pursue creating models that are antagonistic and kind of designed to challenge me and maybe make me uncomfortable. Because I think that sometimes the best antidote to a creative rut is working with someone who pushes you to do things that you never imagined you could. So thanks so much for your attention.
First of all, great job nailing a strange loop talk. This is the most strange loop talk I've ever been. Fantastic. And I guess this is, I don't know anything about training models, but would you think that training on like ballroom or something more structured with like rigorous rules, do you think the computer would have an easier time with that, or would it just be super boring because it's so structured?
It's such a cool question. Thank you for that. Yeah, because I've really trained on just myself as an input, and my background is mostly in like Western, ballet, modern, postmodern kind of movement styles. And it's, I think one natural next extension would be applying to, whether it's ballroom or Indian classical dance or other movement styles that have maybe a more codified movement language. It would be really interesting to see what that looks like. I have no idea what it would look like in this model. Maybe one of the reasons why it's so interesting to explore this space is that of the 256 dimensions in my latent space, I'm not really sure what any of those dimensions really represent. And maybe with a more codified movement structure, you could actually start labeling some of those dimensions. That would be really cool to see. Thank you.
Hey, yeah, I want to echo that's such a cool talk. So in the graph encoding, it seems like it found like correlations between different parts of your body. In either one of those encodings, were you ever able to find like, I don't know, parts of the submanifold that represented like were actually movements isolated to one arm that were like local to each other in the graph representation, if that makes sense?
Yeah. There were a couple instances where it really fixated on feet. Like one edge type was just a single foot and all of the connections within that foot. And I think it kind of depended on what part of the movement data set it was looking at and where the articulation was going on. I did expect it to pick up more on skeletal structure. I thought maybe you would only find like skeletal relationships. That was one of the inputs to the graph model, is each edge was labeled with a 0 or a 1 based on whether or not it belonged to what I described as the skeleton. So it had a little bit of that information already. But yeah, for the most part, I felt like it picked up on these like crossbody, and only a minority of the edge types were really located in one single area. Thanks.
First up, great talk. You mentioned the use of this research for preservation, right? Mm-hmm. Any words on what other dancers are not familiar with machine learning or data representation in general? I mean, any thoughts on how this can be made more general purpose for non-engineers?
Yeah, it's an interesting question, because when I talk about this work to technology or science people, people seem to be really interested in it. When I talk with choreographers and dancers, by and large, people are kind of like, why? We have existing practices in the dance world to kind of, preserve someone's legacy and someone's ideas, and those can't be captured in a machine learning model like this. They're captured in language and in relationships, and when I've learned pieces that are from choreographers, it's often taught by someone who has already performed that piece or someone who trained in their company, and there's kind of this oral history that's really valued in the field. So I think it's personal. It works for me because it feels like it authentically captures some part of my process, but that might not be true for most choreographers. But I wonder how that might extend to other creative types who also have this like technology bent, and maybe it'll be useful in that sense too.
Do you think this could be used for something like measuring the effectiveness of that oral history? Like if you can capture movement now and in 20 years see if we're playing a game of telephone with how we're capturing the history of dance?
Yeah, interesting. I mean, we definitely are. I did a piece a few years ago where we were learning from, the piece hadn't been performed in like 40 years. We were learning from these black and white video pieces with no audio, or like the audio had been like, damaged in some way, so it was out of sync. So like kind of by construction, I think every new iteration of a dance piece, you can't perfectly capture it. But to your question, I think one way that I didn't put on this bullet point list is, I think it could possibly be used for like teaching choreography in kind of like a gamified structure. Like, here's the latent path of my choreography, now you have to try to match that as best as you can. So, to the extent that you want to measure correctness of choreography, you may or may not be interested in that, but I could imagine applying it in that kind of structure to share your material with someone else.
Hey, so first up, great talk. There's one video example in here, but I'm particularly curious about, which, first of all, disclaimer, I don't know much about VAEs. It was from that first half of the presentation. But I'm just trying to wrap my head around how exactly the input space maps to the output space in that, that one example you showed where there was a choreographer and there was a live feed of where their current movements were in the latent space. I'm just curious, when we're looking at that like two-dimensional representation of where they currently were in the latent space, is that just a function of their current position, as in, regardless of what they'd done 5 seconds ago, if they were in the same pose now, they'd be in that same spot in the latent space now? Or is the distribution over something more like a stochastic process, wherein, the exact thing he did 10 seconds ago would have affected his position now, even if he were in the same position now in two different scenarios?
Yeah, totally. So the performance with Raymond, I'm trying to remember, it may actually have been a pose space, like a space of poses rather than sequences, in which case it was responding to, at a given frame of time, what does that correspond to in the model? And so that might have had better inference for the purposes of his work, where maybe waiting 5 seconds to get each movement sequence and then getting input from the model wouldn't give him enough time. So we played around with both models. We had kind of the sequence-based model, which is what I used for most of this talk. But we also have a model of just poses. And so you can imagine tracing any line through the latent space there and then constructing a sequence of those poses. But yeah, we loaded the trained model into like a TensorFlow.js system, and we were able to kind of ping that in real time with the motion capture suite.
So in the video that we're looking at, it looks like it's generated based off of like you had planted one foot and then pivoted on the ball of the foot, but based on the way that the space is recorded, it looks like it's always centered at 0, 0. Do you think that the lack of absolute positioning kind of confused it in that it sort of thought, hey, it's fine, Mariel can just arbitrarily start spinning in place? Like, do you think it could become more robust with absolute positioning or absolute offsetting?
Possibly, yeah. It was one of the pre-processing steps that we included to let the model focus on just the body's position, was kind of averaging out XY positions in the overall data set. So it sort of looked like I was on a treadmill in all directions. And I found that was useful just for getting better results for the actual generated sequences. But it does have this interesting side effect of looking like I'm ice skating or something. Like there's very little friction at times in the generated outputs, and that's probably a result of some of the pre-processing that we applied.
Okay, thank you so much. That was a great talk.
Thanks, guys.